So what I want to do today is we want to talk about presentation of scientific data. I'm not going to talk about how to actually do the graphing on Excel. I presume you've learned how to do that. If not, there's lots of YouTube videos out there. But I really want to talk about how do we present the data. You will be writing reports. You will be writing memos throughout the semester, thinking through what is the best way to present the data. So this data that we're presenting can include individual facts. It can include statistics. It can include items of information. Some of this in the class you will generate from experiments. Other data you will generate from the sampling plans and the sampling that you will do and the analysis that goes along with that. And then the question is, we want to provide the data in a form that's most understandable to the reader. So do we present it in text as a written report? Do we provide it in tabular form as a table? Or do we provide it in graphs? So when you're thinking about presenting the data, I want you to think about that. How best do you convey your message? And what message are you conveying? Now, you can prepare it as a paragraph. And that can summarize quantitative data, qualitative data from your study. You went out to the Red Cedar, you monitored pH, temperature, nitrate, phosphate, and you found that the range in nitrate levels along this one reach of the river ranged from, let's say, 0.05 to 1.36 milligrams per liter. Now, that provides some context. Doesn't provide all the data. So with that example, it gives you a sense of what the range is. What doesn't it tell you? That example, you've got a range. What doesn't it tell you in that example that I gave you? It doesn't tell you where. It doesn't tell you how deep I sampled. It doesn't tell you what the individual values were at any sampling location. But it gives you some indication of the range. Now with your results don't provide any judgment. I haven't discussed are those levels high? Are those levels low? Is the body of water eutrophic, mesotrophic? So that information isn't in there. That information belongs in the discussion. So your results are just simply the tabular or chart form of the data. And the other thing to be careful is not to duplicate data. So if you present the data in a table, there's no need to present that same data in a graph. It's just duplication of essentially the same information. So think about what's the best way, again, to convey the information. So you can see here, I've presented some data, and you'll notice that most of this data actually came from 2020. I developed this last year, and I actually never presented it in class last year. I updated it a bit this year, and you can see there's a lot of COVID data in here. It's on our minds last year. It's still on our minds, unfortunately. But so we have a data table. So the independent variable in this case, X, is date. Okay. And the number of cases, and these are cumulative data, are compared with data on reported data on a particular date. And what I did was this year, I went back and I added the data for 2021. So we can compare, we can look at this and we can go, okay, in March of 2020, we had at that point 3,657 cases in Michigan. And then if you look a year later, we have 652,569 cases reported. So we can compare across the dates. And it allows a pretty easy comparison, and it's an accurate comparison because we have the data right in front of us. Think about, are there other ways that we could report this data? So we could use graphs. Again, always think about this question. What are you trying to show? What question are you trying to answer? And that when you're thinking about which graph you can use, think about that before you even think about which of those Excel graphs you're going to use. So graphs are much more visual. We can compare sets of numbers. We can compare sets of topics. And different graphs will allow us to show different things. So Scatterplot, your typical XY graph. Okay. Type of graph you've been probably plotting since elementary school. So this shows how the data is distributed between two variables. So we have some variable X, some variable Y. We could plot the inches of rainfall per time that occurred this afternoon. We could actually measure inches per hour and plot that. It's especially good if we have large data sets, and it allows us to quickly identify points that are outliers. So for instance, I can use this for a calibration curve. The nitrate test that you'll use was actually designed for seawater, but you're not going to be testing seawater because we don't live near the ocean. So we're going to test freshwater. Well, I had to adapt that test so that you could use it. Well, one of the things that I did was, first thing I had to do was a calibration curve. So I measured the concentration, made a known concentration of nitrate, determined the concentration with the test kit. So in this case, it's known concentration of nitrate. This is the measured concentration. I want to know if I have a linear plot. I want to know if the slope is 1-to-1. I want to know if there's a linear range. So for instance, there's a linear range, and then you find that the plot curves over and it's no longer linear. So it tells us, okay, what range can we work on? I had to look at this to determine what concentration of seawater. So what concentration of salt did we need to add? I found that in a freshwater, I got a plot that looked more like this. So the concentration that I measured was dependent on the salt concentration. So it allows you to look at these types of factors, plot them, determine if these two characteristics are related. It allows you to assess reproducibility. So if I do the test on another day, same concentration of salt, hopefully I get a plot that looks something like this. And I know that I have reproducible data. One thing to make sure you remember is that correlation does not mean causation. So simply because there's a relationship doesn't necessarily mean that that relationship or that factor is causing the observation. Another thing to think about is, how do you present the data? This is the exact same data. They're both scatter plots. The difference is I have a linear scale and I have a log scale. It's harder to see that if I look at the blue are COVID deaths, the brown are confirmed cases. It's harder to see that the trends for death mimic that of cases if I look at the first graph. If I look at the second, it's a little more obvious. You can see that leveling off. You also see that it's exponential. So we have an exponential increase in that first couple months. And then you see that the rate of increase is actually decreasing. Also think about the scale. If we plot, in this case, this isn't cumulative. This is actually the number of cases on a particular day. And sorry, this is both these are cumulative. So it's still cumulative deaths, cumulative cases, but the scales are very different, thankfully. So the cases were up to 12,000, but deaths are 7,000. If we plot it on the same graph as we saw in the previous slide here, it's harder to interpret the data. It's harder to look at the graph and determine how many deaths had actually occurred. But if we can use the secondary axis on Excel, so we have deaths plotted on one axis, we have number of cases plotted on another axis. So now you can begin to see these differences here. And the only difference between these has to do with whether we use a line or whether we just point as a number of points. And in this case, you can see the number of points. You can see I've plotted this just as a line. So Excel has fitted the data. I can also smooth the data. So in cases where you have a large amount of data, you want to get a sense of the trends, but you want to smooth out the variations. So the variations may look much more like this, but I just want a better sense of what are the trends. So in this case, and you can do this easily in Excel, I've just plotted the data and you can see it's a 7-day moving average. Hospitals, I used a 2-day moving average because it didn't vary so much, and then daily deaths, a 7-day. I've lost some data in here. I've lost the large variability. But in some cases, it's easier to see the trends. So I can plot the data in this way. You can also use straight lines versus smoothing. So again, this is actually recent data. And I plotted this because I started plotting this actually back this summer. And one of the questions I was asking myself in plotting this was, how does the current situation compare with the situation last summer? So I started this back in June. So it was actually back in June when President Stanley made the statement that things were great and we would be fully in person. So I went, well, okay, so where are we compared to last year? Last year, what decisions were we making? And then I was asking, well, is it getting better or is it getting worse? Well, what about hospitalizations? I actually had another plot in here, another graph in here, which I didn't include, which calculated the number of cases per 100,000, but took into account the percentage of fully vaccinated individuals in Michigan. So the question was, what is it if we just look at the unvaccinated population? What last year, no one was vaccinated. This year, roughly about 48% of residents of Michigan are fully vaccinated. Well, how do they compare? So what do we see? And really the only difference in these two plots is one is plotted as a straight line, which you can see better here. So you see it's just a straight line. Here the Excel tries to smooth the data, so it's not quite a straight line. So if you're looking at this, what do you see? If I were to present this to you, what conclusions could you make from this graph or these graphs? So the blue lines are for last year at this time. Red lines are for this year. Dotted lines are hospitalizations, and the solid lines are weekly averages in cases. Exactly right. When you look at it this way, in terms of the number of cases per 100,000, or the number of hospitalizations for that matter, we're actually worse than we were last year. And it's even worse. You can pretty much double or almost double these numbers if you look at the cases. If you look at essentially dividing it by 50,000 being that population that is not vaccinated. And then we can make some decisions from this. What do we do? So, well, it seems better. On the other hand, like I said, when you look at it, it actually looks worse when we compare it to last year at this time. We'll look at some other data so we can kind of get that in context. We can also ask the question, are the number of deaths related to the number of cases? Now, this is actually for a particular day. So on day X, the reported number of deaths related to the number of cases. I'll answer the question, Blaine, in just a second. Okay. And the answer here is no. And actually, if we looked at the data more carefully and we looked at hospitalizations, deaths, and cases, you find that hospitalizations, the number of hospitalizations is shifted from the number of cases by about 2 weeks and deaths by another 2 weeks. So actually, if we had plotted the number of deaths on a particular day 4 weeks after the number of cases, we might see a correlation. Good question. Okay, was the decision to move in-person lectures evidence-based then? Not if you look at last year. If you look at the year as a whole, which we'll look at some data for the whole year, you'll see that the number of cases right now is significantly lower than it was earlier in the year. But if you look at the decision, when the decision was made last year to move to remote learning versus the same time this year, no. If you just take that as a snapshot, no. The big difference is vaccinations and the thought that the vaccinated population is relatively well protected. What happens after Saturday's game? I don't know. Because as I said, only about roughly, I think 48% of Michigan residents are fully vaccinated. Okay, we can also use bar graphs or column graphs. And these are useful when we're looking at different categories, and we'll see that in just a bit. Okay. And the y-axis is often frequency or some value. Now, these allow us to look, for instance, at differences. We could look at food preferences. So we could compare food preferences, let's say, of the entire class, different type of foods. How many people prefer pizza? How many people prefer, I don't know, chicken nuggets, tacos, whatever. We could determine that at the beginning of the semester. We could determine at the end of the semester. We could determine it. So we could look at trends, for instance. It's a nice way of summarizing a large data set in visual form. It's better than tables for clarifying trends. The challenge is, and remember this one, I'll show you this in just a little bit, how it can be easily manipulated. And often we need an explanation. So, for instance, here is a bar and column graph. And yes, I've plotted a lot of data. This is actually for last summer. And it was looking at the number of COVID patients in critical care, so basically hospitalized, in Michigan, in different regions. And it probably would have been better. Well, actually, probably would have been better if I had color-coded my graphs with the color codes here, because it would have made it a lot easier to read, wouldn't it, than having the different colors instead of using Excel's decision on colors. But it allows us to look at which regions at any particular point in time were the greatest number of patients hospitalized. So you can see that region 3, which is this region here, had throughout this time period the greatest number of hospitalizations. You can also see how it decreased with time, and it decreased, for the most part, it decreased with time for most of the region, so we can see that. We can compare for any point in time. We can compare regions. So it allows us to summarize a significant amount of data in one plot. I mentioned that it can be manipulated. This was a plot actually published by the state of Georgia, seemingly showing that there was a decrease in the number of COVID cases. I want you to look at this plot and tell me what you see. I'm going to give you a few minutes or so to look at it. Look at the plot. If you look at it right away, wow, okay, significant decrease. Is that the case? So there was a lot of blowback on this graph. Exactly, the dates aren't in order. So if you look at this, and they published it, wow, number of cases are decreasing. Until you look at the fact, the scale. So can you manipulate data? Yes. Do you want to manipulate the data? Should you manipulate the data? No. This bar graph is straight. It's just a screenshot off of the MDH Health and Human Services, Michigan Department of Health and Human Services website. And this is plotted as a bar graph. Why a bar graph and not a scatter graph? What's the benefit here? Why choose a bar graph? Why not a scatter graph? Look at the data. What are they trying to convey? So one, okay, they can show confirmed as well as probable. It would be much more difficult to show that, and to show that as additive if they used just a scatter graph. So here you can really see these differences, the total, essentially, as by plotting it this way, it allows you to see the trends. It's not looking like there's outliers. It really does allow you to see the trends. You can see the differences, okay? So here, first onset in Michigan, was late March. Now, here is when the decision was announced during the summer that we would be in person. We can compare that to where were we last year, which is right around here. So if you look at it, okay, in terms of where we were July of 2021 versus where we were in July of 2020, we were far better off in July of 2021 than we were in July of 2020. Now, if we compare where we are here now, I'll just kind of right here to where we are right here, you can see that we are worse off now. Where we will be in the next few weeks, will we level off? Will we continue to increase? I don't have an answer. We can continue plotting and see, but it allows you to see these trends. It allows you to also see where the peaks were. So you can see that things were pretty bad last fall. They were actually pretty bad again in spring. And hopefully we don't end up back there. Okay, but you also see what happened right here is when Delta became the predominant variant in Michigan. So we were actually doing quite well until Delta became the predominant variant. And then you really start to see this significant increase. Now we can also adjust the scale, and actually on the MDHHS website, it allows you to adjust the scale. So for instance, in this case, what I did was I adjusted the scale and looked at the number of cases and in 2021, okay? And difference here, notice the scale here and the scale here, okay? The big difference is this is in all of Michigan and this is in Ingham County. So you can start to see too, or is Ingham County trending the same way as the entire state? Is it quite different? You could look at it for any one county, so you could start asking those questions. So Wayne County, Allegan County, do they look at, again, how do they vary? So the question is, what are we asking? Here, I'm asking the question, does Ingham County trend the similar way as the state of Michigan? And you can see it pretty much does. Another type of graph that I actually had never used until last year, and it was actually a colleague that had suggested plotting some data this way. And here, what I was using bar graphs initially, and a colleague was like, you should try using a radar graph or a radar chart. And this allows you to display data in a two-dimensional form of 3 or more variables. So you can see here, I'm plotting the number of cases, in this case per 10,000, in different areas of Michigan and also Michigan, and I'm plotting it over time. Notice this is for last year. So what do you see from this graph? Look at this. This is in a report. You're reading a report. What take-home message would you get from this graph? Think about that. Give you some time to think about it. Back last year, okay, so Detroit has more than any other, okay? And that was really true. Okay, so it really shows Okay, where the spread was the greatest. Okay, so last spring, and you can see these differences. You can see how rapidly COVID was spreading in Detroit. Much greater rate than, for instance, even in Genesee County. Macomb was increasing, but not even as much as Detroit. So it gives you some sense of which areas were the most affected. It gives you some sense of the rate at which transmission was occurring. It also, looking at this, it could give you some sense of where we needed to put the most resources for that population. So we can also use pie charts. Pie charts are often used to examine the part or whole relationships as a proportion. So you can see if we look at the location of cumulative cases in Michigan, this was last summer, you can see it doesn't give you this. This was just the total number of cases. So you can see that about a third of the cases were in Wayne County. So it gives you some sense of where, real quick visualization of, in this case, the concept of a whole and a comparison of the components. It doesn't give you the totals. So it doesn't tell us anything about how many cases there were. There could be 100 cases. There could be 100,000 cases. The graph doesn't tell us that. It just tells us the proportions. And this is a similar plot then for October. We can also use box and whisker plots. So this is a convenient way of comparing data sets. And it gives you some basic understanding of the mean, the median, outliers, gives you some sense of whether the data is normally distributed. So in this case, I'm just going to put the X there. In Excel, an X is used for the mean. Put an X there. Which of these two data sets are normally distributed? This one. So where the X, where your mean and your median overlay one another, it's pretty, at that point, you can pretty much assume that that's a normal distribution. It focuses on a few key statistics, so you lose all the rest of the data. Lacks fine details, but it gives you a nice overall picture and allows you to compare data sets. So data here is actually the raw BOD at the East Lansing plant. It's actually for August 2007, November 2007, February 2008, and May 2008. And it's just data is plotted on Excel. And what you see here, okay, is, as I've said, here is the mean, here is the median. Okay. This is the upper limit of the third quartile. This is the lower limit of the first quartile. This is our minimum, and this is our maximum. Okay. Now, Excel will also plot outliers, so you'll see sometimes some data that are outliers. And the way that Excel does that is, this is 1.5 times what is referred to as the interquartile range. So if it's outside of that region, then it's considered an outlier. This is not a test for outliers. It's just simply the way that Excel shows the outliers. So for example, in this graph, and I'm just going to put the numbers on here for an example. Let's say this is 23 corresponds to 23.75 on the y-axis, and this as 5.25. Okay, so that's the first quartile and the third quartile. Anything to determine what is an outlier is 23.75 plus 1.5. This difference here is 18.5. So this is equal to 51.5. So any value greater than 51.5 is going to be marked as an outlier. We're going to do the same thing, but here we're going to take 5.25 minus 1.5 times 18.5, and that is equal to minus 22.5. So any value below 22.5, negative 22.5 is considered an outlier by Excel. So when you look at the plot and you see these little dots, the circles, open circles, that's how the outlier is determined. The last thing that we can use that we'll talk about are heat maps. So these are useful when the data are geographically linked. So there's some geographical location. This is the COVID heat map for Ingham County from the Ingham County Health Department. And what do you see here? Okay. Where there's dense transmission or number of cases, you see those are marked in yellow. And then kind of a bluish purple are the fewer numbers. Okay. So these typically are based on some sort of a density. So they're really isoarithmetic density maps, or kind of think about contour lines on a topographical map. And we can look at data. We can basically, from the data, this is actually using zip code data. So what they've done is they've taken that zip code data for a particular zip code, and they've taken the adjacent zip code, and they do what's referred to as kriging, which is a statistical smoothing technique to try and link that data by, as I said, contour lines. The results are very much dependent on the density of the data. So how much data, okay, this would look very, very different if instead of using, actually let's use the census data, so it gets to a pretty fine detail. If we were to use zip code data, you'd see a very different map. Or if we were to use city boundaries or township boundaries, you'd see a different map. So it's very much dependent on the density of the data, the scale that you're using, what these maps actually would look like. The other issue, and you don't see it so much on here, but so if we have a point, for instance, up here, and that's a very high point, a high value, that can really skew the kriging analysis, and it may look like maybe that's an outlier. Maybe there's some phenomena that's happening that value is really high. Maybe it really isn't distributed, but it's going to look like it's distributed on the map because of the way the kriging is done. So you have to be very careful with these when you're generating the heat maps, how you're generating those. Okay. If we had time, I was going to have you do a breakout rooms. We don't have time, so we're just going to skip that. So as you're thinking about presenting your data this semester, think about, is the data skewed? How does the median compare to the mean? Are there outliers? Are they temporal outliers? Are they outliers, for instance, based on location? Are there temporal changes? is there a relationship between X and Y? And if you think about that, think about, is there a reasonable explanation for that relationship? Are you looking at predicting future values? Do you have the data to do that? One of the most important things to think about is, what is the story you're trying to tell? What is the message you're trying to convey? Not every type of graph is going to help you do that in the same way. So how can you convey that information? And then, who is your audience? So we'll end there. As a reminder, tomorrow, those of you that are in section 1, we will be on Zoom. We're going to do health and safety plans. You're going to use your safety training that you've done to create a health and safety plan. Those of you that have done this in 483, you'll have done it once, but you're going to focus a lot more on the actual sampling, going out and collecting samples, being in the lab, the hazards in the lab setting. We'll also look at, you can add COVID. Thursdays, section 2, on Thursday, you'll do the same thing. Section 3, you can attend either section, that's fine. If you cannot attend either section, see me, and we'll figure out when you can do, and hopefully there is a group of section 3 students that can work together on that so that you don't have to do it alone. Any questions?